Hello everyone. Today we discuss monotone and inverse functions. In the previous chapter, we already discussed monotone sequences, and we saw that monotone sequences are very special. We see in today's discussion that a monotone function is also very special. Let's start with a definition. Throughout this section, we consider a function f from some subset A to the set of all real numbers. This function f is said to be increasing if for x1 smaller than equal to x2, f of x1 is smaller than equal to f of x2. F is said to be strictly increasing if the inequality is strict. That is, if for x1 smaller than x2, then f of x1 is smaller than f of x2. Similarly, f is said to be decreasing or strictly decreasing if we reverse the corresponding inequalities. That is, for x1 smaller than equal to x2, then f x1 is greater than equal to f x2, and f is strictly decreasing if for x1 smaller than x2, f of x1 is greater than f of x2. Now, a function is monotone if it is either increasing or decreasing. So this is just a natural extension of a monotone sequence. A sequence is a special function. So we can define the monotonicity of a function accordingly. Now let's consider inverse functions. Recall that a function f has an inverse denoted by f to the -1, even only if f is injective. In other words, it is 1-to-1. That is, for x different from y, f of x is different from f of y. Please note that a strictly monotone function is injective and just has an inverse automatically. Now, the main theorem states the following. This is called the continuous inverse theorem. Let I be an interval in a set of all real numbers, and f a function from this interval I to a set of all real numbers. Let's further assume that the function f is strictly monotone and continuous. Then it has an inverse denoted by f to the -1 by the previous discussion. Moreover, this inverse is strictly monotone and continuous on the interval j, which is the image of the interval I under the function f. So the content of this theorem is about the monotonicity of the function f to the -1 and its continuity. Here is a sketch of the proof. We consider the case that the function f is strictly increasing. First, we show that the function g, which is the notation for the inverse of the function f, is strictly monotone. We observe that since the function f is continuous, the image of the interval I under this function f is an interval called J. This comes from the preservation of intervals theorems we discussed in a previous section. Now, because f is strictly increasing, f is injective. Let y1 smaller than y2 in J, then y1 equal to fx1 and y2 equal to fx2. We have this inequality because the function f is assumed to be strictly increasing. Now for the function g, which is the inverse of the function f, we have g of y1 equal to x1 and g of y2 equal to x2. Since y1 smaller than y2, fx1 smaller than fx2, we must say x1 smaller than x2. Therefore, g of y1 smaller than g of y2, leading to the conclusion that g is strictly increasing. So the choice of y1 and y2 here is totally arbitrary. With that arbitrary choice, we show that if y1 is smaller than y2, then g of y1 is smaller than g of y2. That's why this function g is strictly increasing. The continuity is left as an exercise for you to do. Now, a very interesting application of the discussed above is the definition of the nth root function. Remember, it is a very non-trivial problem to define a root function. In order to define the square root function, we had to use the completeness property in a previous section. Remember, the square root of number 2 is defined to be the supremum of the set of all real numbers such that the square of each number is smaller than or equal to 2. We take the supremum of that set and we show that by the completeness property, the square of the supremum is exactly equal to 2, and the supremum exactly is equal to the square root of 2. So the problem of defining a square root is already a very non-trivial question. Now we would like to define the nth root function, which works for any natural number n. We're going to consider two cases. The first case is n is even. Let's consider the function f of x equal to x to the n. In general, this function is not strictly monotone. However, this is strictly monotone if we restrict ourselves to a specific interval, namely the interval from 0 to infinity. And you can see the strictly monotonicity of this function from the graph here. That's why it is natural to consider this interval I from 0 to infinity, including point 0. We show in a previous section that this function is continuous. So now we have a continuous, strictly monotone function. We can apply the continuous inverse theorem above to conclude that this function f has an inverse which is monotone and continuous. Denote this inverse function by this symbol f to the minus 1. We claim that this is exactly the nth root of the value x. Why is so? Because f to the -1 of x equal to y, and y to the n equal to x. That's why y exactly equal to the n root of the value x. So this n root function is strictly increasing and continuous from the interval 0 to infinity, including 0, to the interval from 0 to infinity, including 0. We can see the graph of this function from this drawing. The second case is when n is odd. This is actually an easier case because in this case, the function f is strictly monotone for the whole set of real numbers. We apply a similar argument to define the n root function, in this case when n is odd. We can also further extend to rational powers. That is, if m and m are natural integers and x greater than equal to 0, we define the rational power x to the m divided by n to be equal to, first of all, we take the n root of the value x. So this is the function we just defined earlier. And then we take the m power, whatever input we obtained from the first function. And we can define a negative rational power in a very similar way.